All right, welcome to 7.3. This lecture is actually in 3 parts, but today we are only doing part 1. So go ahead and join me for the ride. By definition, a cyclic polygon is a polygon that can be inscribed in a circle. That is, all of the vertices of the polygon lie on the same circle. Okay, so they can all be inscribed on the exact same circle. In task 5.9, Centers of Triangle, your work on Kara's notes on a diagram should have convinced you that it is possible to locate a point that is equidistant from all 3 vertices of any triangle. Therefore, all triangles are cyclic polygons. That means you could inscribe or you could draw a circle that will touch all 3 vertices exactly. Okay? So, based on Kara's work, use a compass and straight edge to construct the circles that contain all 3 vertices in each of the following triangles. Now, you'll have to think about, okay, how did we do that again? And the way that we actually did that is we constructed perpendicular bisectors for the sides, and where those perpendicular bisectors coincide, that's where we can use the point that we can use to draw our circle. Okay, so I'm going to do the first one with you, and then you can do the rest on your own, the other 3 on your own, or the other 2 on your own, excuse me. So I don't have a compass here, actually, so I'm going to kind of guesstimate mine. But there's one, and then let's see. Here's another, approximately. So actually, they coincide with one another pretty well, that point right there. So then, if you wanted to use your compass that goes this length, or really to any of the vertices, and you should be able to inscribe a circle that touches all 3 of those sides. Okay, so mine's not perfect. Yours will look much, much better when you use a compass and a straight edge and actually construct the perpendicular bisectors. So go ahead and work on the other 2, and then come back in a minute. So since each vertex of an inscribed angle lies on the circle, each angle of the triangle is an inscribed angle. And we know that the sum of the measure of the interior angles of a triangle is 180 degrees, and that the sum of the measures of the 3 intercepted arcs is 360 degrees. So what we're looking at is from here to here, plus from here to here, plus from here to here is 360 degrees. That's just basically saying there are 360 degrees in a triangle, okay? So using one of the diagrams of an inscribed triangle you created above, illustrate and explain why the last statement is true. So think about, why is it that those inscribed angles add up to 360 degrees, and that the angles in a triangle are 180 degrees. And essentially what we're looking at here is that, let me clarify some things for a minute. Each of our circles, and let me erase these, or each of our angles, inscribed angles, they intersect one portion of the arc, right? Like we were just talking about. So this intersects this portion of the arc, okay? And then we have C, angle C, that intersects this portion of the arc, and angle B, which intersects this portion of the arc, okay? So essentially, each one intersects a certain portion of the arc, and so since every part of the circle is intersected, we will obtain 360 degrees of arc there. Now, we can make an interesting statement based on this. So let's continue on. We know that the degree measure of an arc is by definition the same as the measure of the central angle formed by the radii that contain the endpoints of the arc. So let me just give you a quick example here of what that means. So if we have, almost a circle, if we have this section of arc, that degree measure is actually congruent to this degree measure, or it's the same as this degree measure, okay? So if this is like 80 degrees out here on the arc itself, on the circumference itself, this will also be an 80 degree measure, an 80 degree angle, okay? So, but how is the measure of an inscribed angle, meaning this angle, how does it relate to the same arc and to the measure of the central angle? Okay, this is something useful for us to find out. All right, so you need to use a protractor to find the measure of each arc represented on each circle diagram above. Okay, so you're finding the measure of each arc, and on your protractor, what you're going to do, here's a little makeshift protractor. What you're going to do is you're going to basically put your center at the center of the circle, and then put this side right here on one of those lines, and then try to match up you should have like either you can make one like a makeshift pencil, use a pencil as your straight line to come out here, but this thing can move back and forth. So measure the angle of the arc itself. So this right here should rest on the arc, and then you're going to move that little guy until it can intercept the arc. And if you have questions on how to do that as well, please feel free to ask in our Google Meet today. And then make a conjecture. So then you're going to find the measure of each corresponding inscribed angle. Remember, inscribed angle is this one right here. And then you're going to make a conjecture based on that data. So go ahead and do that right now, and then we'll continue on in a minute. Okay, so hopefully what you discovered in that process is that the inscribed angle actually has a measure exactly half of the arc and the central angle. So if this up here is 80 degrees, then this inscribed angle should be 40 degrees, okay? So that can be your conjecture for number 3. And for these last 3 proofs, we are actually going to take care of them in the Meet, so please join with me in the Google Meet, and we will tackle them there.